decided to do two of your homework problems. One that both of them we saw in class, but the groups had some questions about them, and so I know we probably all do. So I'm going to go ahead and do one of our ladder questions for related rates, and also the shadow question. Uh, these are both two of the examples that I want you to be familiar with for the topic. This video is going to be a little different. One, because it's me, and two, I'm not going to ask any questions throughout, so just consider this additional lecture. Takes notes on these, and let me know if you have any questions in class. So at the end, there will be a question to give you the points for this video. So I'm going to go through two questions. The first one, again, being the ladder one, and the next one being the shadow one. Okay, so this is number 6 from your homework area in 4.1. There are a handful of classic problems. One of them is the ladder question. This is somewhat similar to the one where two people or planes are walking towards or away from each other. This is slightly different in that some of the stuff is constant throughout the problem, and that has the same issue with the shadow one about what's constant and not, the difficulties in setting it up. Okay, so first thing, we're going to read through the question, and we always try and graph a picture. When we're graphing the picture, we need to ask ourselves, is everything that we're writing down a variable throughout the problem for this related rates idea, meaning is it changing, or is it something constant? That's what you want to ask yourself. So we have a 25-foot ladder leaning up against a wall. So here is the ladder. So even though that's part of the triangle, that ladder is constant throughout, so I don't actually give that a variable. If we push the ladder towards the wall at 1 feet per second, so we're probably pushing from here. So I'm already going to introduce a variable. I'm going to call this length x. And knowing that these are rates, right, this describes dx dt. As we pointed out in class, it's someone pointed out, not me. I'm not very good at this, actually. Remembering to keep track of your negative signs can get you a more accurate answer. So x is actually shortening because the ladder is being pushed up against the wall, and so dx dt is -1 feet per second. All right, it says, and we're pushing this at the bottom of the ladder is initially 20 feet away from the wall. So that length is moving throughout the problem. So we can keep in mind that this is going to be 20, but that's not something we can plug into our equations just yet, because x is a proper variable changing through the problem. All right, the question is, how fast does the ladder move up the wall 5 seconds after we start pushing? So there's this variable side over here also, and the question is, how fast is the ladder moving up this way? And so dy dt is the question that we are asked. Okay, so a lot of groups the groups who worked on this type of question usually had a pretty good idea that we put this together with the Pythagorean theorem. So we can relate these variables by Pythagorean theorem. The length of the two sides added together is the length of the hypotenuse added together. We can square 25, but we can also just wait and see if we actually even need to. So that is our main equation that relates this problem. And we're keeping in mind that we want to find dy dt. Right? Officially, this is going to work like implicit differentiation, tiny bit differently than normal implicit differentiation. The idea is that length x is actually dependent on time. And this one's pretty straightforward. You're pushing it with just 1 feet per second. You could actually make its equation. But the idea is we don't have to do all that work. X, we're treating as a function of time, and so we just need to keep that in mind when we take the derivative. Okay, so we can actually just start the differentiation. So go ahead and take the equation we made and differentiate both sides. So derivative of 2x, the derivative of x squared is 2x, but we're treating this as chain rule, right? So initially we kind of imagine, sometimes a parentheses helps me think about chain rule. So the inside is x, but it's a function of t. So derivative is from the from our power rule, exponent comes down out front as multiplication. So 2 times that function of t, we're ignoring the inside though. New exponent is 1, but then x is a function of time, and so we need to multiply by that derivative. So that gives us a dx dt. These are all, any proper variable throughout this problem is a function of time itself. And it's much easier to not have to describe those functions explicitly. Otherwise, we could just do normal derivatives, but that'd be a lot of work. We can implicitly leave them, and as long as we know enough information, solve the appropriate values. Right, so derivative of y squared, so 2y, and maybe we can just start remembering that that's its own function. We apply chain rule in the implicit fashion, and we get dy dt. So 2y dy dt. Derivative of 25 squared is not 2 times 25. It is just 0. That's a constant. Okay, so we have 4 things in this equation left. An x, a y, and a dx dt, and a dy dt. dy dt is our question. Dx dt is given. X is 20, kind of, and y we need to figure out, but I think that's just a triangle. So I think we can figure all of these out. So doing a little bit of additional work here. So everything seems pretty reasonable. The question had this idea of after 5 seconds. And so it's moving in at 1 feet per second. So it will move 5 feet after 5 seconds. So the x that we actually are going to work with is not 20, but 15. I just got to read the question carefully for that. And so the triangle that we want to solve, we have y squared plus 15 squared. It's going to be 25 squared. So this will solve the y at the time that we're interested in studying. So no calculus, just numbers here. So y squared is going to be, I think 25 squared is 625, 15 squared is 225, so subtract, we get 400. So take the square root of both sides, and y is 20. We only want the positive value there. So the ladder will end up at a height of 20. It'll be 15 feet away from the base when we're looking to study these rates here. And so we can solve here. I'm also going to be lazy and divide everything by 2 initially. And so that will just give us x dx dt plus y dy dt equals 0. Keeping in mind that it's the dy dt we're expected to solve here. So x at the time when this is happening is 15. Dx dt throughout the problem is a constant -1. Also at the time we're trying to study. Y that we're trying to figure out, our y at the time we're trying to study is 20, and dy dt is the question. So then dy dt, so then that's going to be -15. So we add it to both sides, we're going to get 15, and then divide by the 20. 15 over 20 is 3/4. This is a rate now, right? The amount that y is changing per unit time, dy dt. And so it's going to have the same rate, the same units as whatever dx dt would have been, which was feet per second. So it's moving a little slower at the moment than dx dt. And if you would like, you can check with some other values, move the whole ladder in more, ask yourself, is it moving slower or faster? I'm not actually sure what that relationship is. It might be interesting to think about. So how does dy dt change throughout the problem? Is it always, is the rate, always increasing? Is the rate slowing down? Is it have like a curve nature to it? Is it like moving fastest somewhere in the middle-ish? I don't, we can plug in a bunch of different values. You can experiment if that maybe helps you think about it. So this one was Pythagorean theorem to solve, some sort of distance one. But this time the ladder makes this makes the hypotenuse constant throughout the whole problem. And so that's, just make this one a little shorter than some of the other distance ones. Right, the other one that I wanted to cover was the shadow style problem. Happens to also be triangles, but similar triangles, but doesn't quite work out like the similar triangles from the volume question we saw in class. So this time, this is number 10. There's a similar number 11 that uses the same prompt, so hopefully you can use this to help you out. So we have a 6-foot tall person walking away from a 10-foot tall lamppost at a constant rate of 3 feet per second. What is the rate the tip of the shadow moves away from the pole when the person is 10 feet away from the pole? And honestly, all of our groups drew the correct picture, started the correct math, but if they also looked up the picture in the book, it kind of put all of us on the wrong path. And so here's what the book gives us as a guide. The lamppost is 10 feet tall. The person is 6 feet tall. They'll be 10 feet away from the pole. And this is the variable out here. I think they used x. Okay, so what's actually misleading about this picture is that more things are moving and there actually needs to be more variables than this specific picture. So this is the lamppost, and so it's shining the light this way. The bottom is, well, the person's shadow right now is x, and this is the person right here. So this piece here is their shadow. Okay, so the person is moving away from the lamppost. So they are not always 10 feet away from the lamppost. So this is more properly, the base of the lamppost is its own variable. Which will be 10 when we want to study the problem. We may or may not need to know the value of x throughout the problem, so we don't need to solve that ahead of time. So this is going to solve with the structure of similar triangles, but we need to keep in mind that that's its own length there. And the way the question is worded, it says, what is the rate the tip of the shadow moves away from the pole? So all the way back to the pole. And so that's actually its own variable also. There's a simple relationship there, that length that I'm just calling z. Maybe we should make sure to label our variables something that makes sense, but we can also just label them random letters. So z is just x plus y. We can leave x plus y, but the question is asking for this length here. So it says, what is the rate the tip of the shadow moves away from the pole? So the question is actually this variable dz dt. So it's not quite dx dt. That would be the rate that the shadow is moving away from the person. And it may or may not be the same, because the person is also moving away from the pole. Maybe it's a quick addition or subtraction of those rates, and so maybe the answer at the end would be very similar, but we have to check all of those to be careful. All right, so now we can set up a pair of similar triangles. So I'm going to outline one of the triangles. We have this first one here. And so if I divide its two lengths, I can construct a similarity relationship. So I can say something like 6 over x, so the person's height divided by the base. And then that would be similar to 10, right? Similar means there's a ratio there. 10 divided by x plus y. Or possibly z. The question did ask us for effectively dz dt, and so I probably should make that z instead. So it's 6 over x is 10 over z. Okay, I didn't take the time to label some other information. I did get distracted with the equation, which I think a lot of groups did also. Okay, let's go back and read carefully. The person is walking away from the lamppost at a constant rate of 3 feet per second. So we've labeled all of the proper values with variables. We have the person's kind of the shadow length, x, the person's distance from the pole, y, and the whole length, z. And they're related, but they're all possibly their own variables here. Everything is changing. So the question asks, or the question gives us that it's a constant rate, that the person is moving away from the lamppost. That's the y variable. So we were given dy dt is 3. Okay, so I just changed my equation to x's and z's because I knew I needed z. But I think I need to make another change because I'm asked for z, but I'm given the rate of y. I don't think I know the rate of x, and so I can't have x's in my equation, essentially. I can have y's and z's because I'm asked about z and given information about y, especially the rate, dy dt. So I will need to resolve and eliminate that x. So if I solve for x, that is y, sorry. So solve for x by subtracting y, and we get that x is z minus y. And I can replace the x in the equation with that. Okay, now I can solve, probably be able to take a derivative from that. I'm sorry, not solve, I can clean it up, take some derivatives. I don't really want to take a derivative just yet. So I can do 6z cross multiply here is equal to 10 times z minus y. I could probably distribute, that seems like it'd be helpful at the moment, 10z minus 10y. And to keep everything positive, I can combine like terms. I'll add 10y to both sides and subtract 6z from both sides. And then this looks much nicer to take a derivative of. So I think I'll take a derivative here. So take a derivative of both sides. Right, 10 is just a constant, so that'll factor out. Derivative of y is just 1, but it's a function of t. So 1 dy dt, which is just dy dt. And same thing on the right-hand side, derivative of the 4z, 4 factors out. Derivative of z is 1 dz dt, applying chain rule using implicit differentiation. All right, so this will allow me to solve for dz dt with knowing dy dt. Really odd before I plug that in, just to highlight, this didn't use the fact that we were 10 feet away. Sometimes there's so much structure to the problems that we don't actually need all the information given. It's not very common, but sometimes that does work out. So we have dy dt is 3. And so solving for dz dt, if I also divide by 4, and so dz dt is going to be 30 over 4, which is 7.5. I think the units were feet per second. So 7.5 feet per second. So moving quite a bit faster than the person. You know, if you've ever looked at your shadow can move really quickly because often, well, sometimes your shadow is, I think in this scenario, the shadow would be quite a bit bigger than the person, and so it's moving quickly. Maybe. You could plug in all the numbers to really get an idea, right? But if you sometimes look at your shadows, they look funny. Sometimes they're really small, sometimes they're really big, and sometimes they can move a lot also. And so what was a lot different about this was that the book actually did set us up poorly for this problem. They actually gave us a picture, which was helpful. But then, if you look at the picture in the homework area, the value for y is actually just written in as 10. But that's not constant. Right? The person's height and the lamppost values are constant. But everything else is actually moving. And then when we go to label the 3 feet per second, we might label the wrong value in this scenario here. So this is the shortest way to set it up using related rates. I doubt that writing it as Pythagorean theorem, it might be possible, but pretty difficult. But if we label everything appropriately, it could work. I didn't try it. You can try that yourself. So hopefully this helps with some further examples of related rates, and we'll have a little bit more class time to talk about these. All right, I'll see you around.